This is now recording. We're going to be starting to look at ionic bonding in a bit more depth. All right, we know what ions are, but now we're going to actually have a look at the ionic bonds themselves and what they mean, what they can be used for. So hopefully I'll make that clear. So ionic bonding. Ionic bonding is the bonding between metals and non-metal atoms. We know that part. A non-metal, right, have a high electronegativity, and they tend to take electrons away. They forcibly take those electrons. They have that pull, that strong electronegative pull. The metals have low electronegativity, so they lose those electrons. In most ionic reactions, the non-metals tend to take enough electrons to make 4 pairs of electrons in their outer shell. So in the outer shell, they want 8 electrons buzzing around, 4 pairs of them. In most ionic reactions, all right, the non-metals will take that electron to fill their outer shell. So here I've got our old faithful standard table salt, sodium, and chlorine. Now, sodium has 1 electron in its outer shell. It's in group 1, we know that. Chlorine has 7. So to get it up to 8, chlorine's going to take that electron. It's going to go over here. Chlorine's going to get a -1 charge. Sodium's going to end up with a +1 charge because sodium now has 1 less electron than it has protons. So overall, this particle has a charge. And once those charges are formed, these two particles will come together because positive is attracted to negative. The metals lose their electrons in their outer shell. I will keep saying it. We all know it. And our group numbers can tell us what charge they form. In group 1, +1 ions. So hydrogen, lithium, sodium all form +1 ions. Group 2, 2+ ions. Magnesium, calcium. And of course your group 3 will form the 3+, such as aluminium, which we used before. Aluminum if you're watching it in the States. But aluminium, okay? Aluminium will form a 3+ charge. It is in group 3 and is a metal. The transition metals, on the other hand, that's that bracket from over here, which includes scandium all the way to zinc, and then yttrium all the way across. Those transition metals tend to lose their 2 outer shell electrons first, and then they start to lose some of their extra electrons in the 3rd shell. They're a bit weird. That's why we call them transition metals. They change quite a bit. And what happens is, if we look at iron, iron's electronic structure looks like this. 2, 8, 14, and then a 2. There's a reason for this, which I'll go into in year 12. But just be aware that what's going to happen is iron will first lose those 2 electrons to form a 2+ ion, which we call the ferrous ion. Then it'll lose 1 more electron to form a 3+ ion, which we call the ferric ion. Okay, the reason is there are a bunch of sub-energy shells in between those 2 shells, and as a result, to reach a stable configuration, it gets rid of the first 2 here and then 1 to get to an even number of pairs. It's a bit strange, but that's just how it works. I'll leave you on that slide there.
Is this up on DayMat?
I'm going to put the notes up on DayMat, and then I'll put the video up there as well so you can follow along. What I'm going to start experimenting with is doing office mix. Have you heard of that? No? All right. Basically, I can put a little webcam video of my face on the slide presentation, so you actually get the slide with my face explaining things. All right. Well, that's our next stage. So we'll see how it goes. Not yet. OneNote is in the process. It is actually quite useful because then you could edit your things on OneNote. So say you were doing your your assignment, you can have the draft there, and I can see what you're working on, and just.
And you don't lose it.
No, and I can give you comments on in real time, basically. All right. So those are the kind of charges we're working with metals. If we look at non-metals, they gain electrons to fill their outer shells, forming what we call monatomic ions, such as, if we look at group 7, our halogens, fluorine, chlorine, and bromine will form fluoride, chloride, and bromide. Notice I'm saying "ide" at the end. Saying "ide" at the end. I'm going to turn this lights off. It's a bit better. Now you can probably see the notes on the video, which is probably a bit handy. Group 6. Remember, 6 electrons in the outer shell. They want to make it up to 8. They're going to form an oxide of a 2- charge or a sulfide of a 2- charge. They're gaining electrons. They're gaining negativity. Group 5s form the 3-. That's your nitrogen and phosphorus.
So non-metals always
When they're on their own, yeah. But non-metals can form complexes, which we call the polyatomic ions. But we'll get to that later. But just in terms of using elements, they form these ions. So if we look here, I've got sodium's electronic structure, neon's electronic structure, and fluorine's electronic structure. Sodium has 1 electron in the outer shell, neon has 8, and fluorine has 7. So because of this, sodium's going to give its electron to fluorine. Neon's not going to have any word of it because neon's already happy with its 8 in its outer shell. It's a noble gas, that's why they don't react. And you'll end up forming sodium fluoride because those charges now will then attract each other together. So they'll have complete shells, but resulting in charges that attract the atoms.
And then the electrons get too close together and they don't actually touch, so they're like walk next to each other.
Oh, the electrons, yeah, they don't. No, they're not going to touch. They'll repel, but they'll get into a spin. Quantum mechanics start to apply when you get into that level, but. So, if a group of atoms has a charge associated with the whole group, and this is what I'm getting at, then you get a polyatomic ion. The polyatomic ions that you need to learn, at least by the end of semester 2 this year, I would like you to be familiar with sulfate, carbonate, bicarbonate, acetate, ammonium, sulfite, phosphate, nitrate, and hydroxide. I've got them on the board. I've got them in the room. I'll give you a table. The one you'll use most often is a hydroxide. There's a -1 charge. Sulfates, particularly when we're using sulfuric acid, will come up quite a bit. And nitrate this year. Yeah, nitrate comes up quite a bit when we use salt solutions. Okay? Nitrate has a -1 charge. These are polyatomic. They've got these complexes of ions. So if we look at phosphate here, the phosphate's interesting. It's a double bonded oxygen on top, and then 3 single bonded oxygens with negative charges on them. Right? These are just some of the ways in which these atoms arrange themselves, and it results in an overall charge. Strong forces of electrostatic attraction hold these ions together in what we call a 3D ionic lattice. If you've got a lattice, you end up with a crystal. Okay, salt exists as crystals when it's solid. Powders contain microscopic crystals. If you've got an ionic powder, you've got microscopic crystals. Copper sulfate, some of you would have done this with me in year 8, where we made copper sulfate crystals like that. Remember those blue crystals we made? Yeah. So they form these lattices. And what do I mean by lattice? Well, it's a repeating unit. And I'll draw it on the board in a minute. I'll get you a table of these, okay, for you to keep and glue in your books. So the table will look like this, and I'll print it off for you. All of this will go up on demo. Everything. And what we'll do when I get OneNote is I'll put the slides themselves up. Okay? We won't look at dissolving yet. So what I want to do is I want to just blank that out for now. And I want to draw an ionic lattice. Now, say you had sodium and chlorine, okay? Or to put it more specifically, you're going to form sodium and chloride ions. Your chlorine is going to be a negative, and it's going to attract a sodium of a positive charge. But the reality is we've got millions of these atoms. We've got millions of these ions coming together. And they arrange in such a way that maximizes their forces of attraction and repulsion to reach a stable, what we call a lattice. So what you end up is repeating units. And so on and so forth. Okay? This is an ionic lattice. You have chloride ions, I should say, and you have sodium ions arranging themselves like so. So if you imagine those particles, they arrange themselves like so. And this is also three-dimensional. So at the back here, you'll have plus, and over here, a minus. Trying to be 3D. Okay. Trying to make it. It actually forms quite cube-like shapes. Isn't as great as I wanted it to be. Okay, it's three-dimensional. But it's the lattice. A lattice is when we have repeating units. All right? I'll leave it there. That's just an introduction to the charges that will form, why they're forming, and the ions that we're going to familiarize ourselves with. We'll explore the lattice in a bit more detail next week and look at how this is responsible for salts being able to be dissolved in water, such as seawater out there. Okay, I'll stop it there.